Big round of applause for him, first of all. So, yes, today I'm going to do an FE problem solving session. For every y belonging to the range, there exists some x belonging to your domain. This is a gem of a problem. Some people are pretty scared of these sort of variations. Enjoy your vacations, enjoy your school after that.
Hi everyone, good evening, namaskar, sat sri akal, salam alaikum. I hope you're all well, fine, healthy, safe. Great to have you. I welcome you all to this amazing session, and this is a special one. I was in Bangalore, and of course, one of our students, and you all know him by name, and he has been helping you all. He is INMO Awardee 2023, ADIT AGGARWAL, and he happened to drop by. And one of the things that we were discussing on YouTube was कि सर functional equation जो है ना वो आपके YouTube चैनल पे बहुत कम है, and so इसको improve कीजिए, because this is one aspect which very few teachers in the country do and teach. That मैंने इसको मजाक में बोला कि why don't you do? He said सर कर लूँगा. And this is the reason we are doing this session. So again, this is an awesome session, awesome initiative taken by Adit Agarwal, and whatever gaps are on this channel is going to fulfill that. Right, at least on functional equations part. So I welcome Adit Agarwal. Adit Agarwal, guys. Okay, so Adit Agarwal, we all know him, and he has been very active on our YouTube channel. He has been helping a lot of students, guiding them, and of course now he is becoming a part of our channel. So big round of applause for him, first of all. And Adit, this is the first YouTube. Of course, you've taught on our camps before, but this is the first time, actively you are involved. I'm leaving apart those congratulatory sessions that you used to have, right? But this is the first teaching session of yours on YouTube, and I wish you all the best. And guys, again, he's prepared a list of 3 problems on functional equations, and he's going to discuss those problems. Each and every problem has something unique about that particular problem, and of course, these are from good sources, good contests which have been done. And over to you, Adit, and I hope you all enjoy these problems. And if you do, please put a like button to this particular session. Adit.
Okay, hello everyone. Hope you guys are having fun. CBSE boards are over. Part of CBSE, so I heard ICSE boards are over. So I hope you guys are enjoying the break that you had between 10th and 11th, or rather, still have. I do hope that you enjoy your journey from now on, because we're going to do JEE as well, or NEET. I'm not going to assume anything. But whatever you do, just make sure that you enjoy it. Okay, don't do something just for the sake of getting a good college. Okay, cool. So yes, today I'm going to do an FE problem solving session. Okay. So okay, first of all, I should probably just give an introduction to myself, shouldn't I? The pen work. Let's see. Yes, the pen works. Nice. Okay. So my name is Adit. As you can see. I'm a 2024 INMO Awardee. So just in a better color. So yeah. So I'm a 2024 INMO Awardee. And to be honest, my biggest passion is functional equations. I feel like people often underestimate how nice functional equations can be, because they tend to treat it as just memorizing some sort of tricks, and they don't realize the actual motivation behind those tricks. So my hope through this session of problem solving is to give you some sort of ideas which you might be able to use in future functional equations. And if you're in for the fun of it, then you're going to enjoy the problems that we have today. They're from good sources, and I'm going to try to go from beginner level to decent level. All right. So here's the first problem, but before that, I guess I'll just run some prerequisites. You should know what a function is, right? You should know what a function is. You should know what injectivity means. You should know what surjectivity means. You should know what bijectivity means. And That's pretty much it. Note that these might not be used in the session, but still, if you know these, it probably means that you're good enough to, kind of start on the session. All right. So our first problem. The one thing about functional equations that you have to know is that most of the time they ask you to find all functions. So here we need to find all functions f, the reals to the reals. Such that this holds. And this is, I think, the reason why people don't like FEs too much. Because at some point in time, it probably all looks the same. Like, I kind of feel the same way about geometry in some senses. In that the problem is always about giving some sort of thing to you, some sort of structure, and then asking you to do some property about it. So yes, I do kind of understand why people don't like functional equations, but at the same time, I'm here to make it fun for you. All right. So just to get started, the source is around TSP. It's an old around TSP, but it's a nice one, and it's going to be a nice start. All right. So we have this equation. What are some things we can start off with? Well, the first thing you notice is that this holds for all x and y reals, right? Now, what this means is that whatever choice of x and y you choose, you can just substitute it, right? And for example, it makes sense to substitute in, for example, y equals 0, right? What happens if you put in y equals 0? You're going to get f of x is equal to f of x squared, right? And so immediately the first thing you see about functional equations is that you can do these sort of substitutions to kind of get more information about the function. So in a sense, this is more of a detective game. Now it's a bit more fun, hopefully. So you have this. And one more thing this might suggest is f of x for x squared, question mark. The reason it's a question mark is we haven't proved it yet. But it seems like it might be true. And if you check the equation, you'll see that f of x equals x squared does work, right? So one strategy that you have is these sort of substitutions. And another strategy that you have is guessing the function beforehand. Yeah? And the thing that happens when you guess the function is you kind of have a way to decide how you want to prove it. Not always, but in some cases. Okay. Now, the main issue with this functional equation is that it seems way too complicated to work on it once, right? So ideally, we'd want to simplify it some way. This is one way to simplify it. But what if we were able to directly cancel off? That would be a nice thing, right? Because if we were able to cancel off two of the terms, then that would mean that we're only left with one term. And one term is much easier to deal with than two terms, or three terms in this case, actually. So let's try to force that to happen, right? What if I force this and this to be equal? Well, you can't force them to be equal directly, but the better way to force them to be equal is to force the things inside to be equal. So if I just force that, so I'm forcing it to be equal to x squared minus y, right? So f of x minus y is this, and x squared minus y is this. So if you solve this, you're going to get y equals x squared minus f of x over 2. Believe? Yes. All right. So what happens if I put this magic substitution in? Well, since these two parts are going to be equal, I'm just going to have f of some stuff equals f of the same stuff plus 4 f of x and our choice of y. In particular, what happens is that these two values cancel. So we're going to get that f of x times your choice of y equals 0. Since we've chosen this as our value of y, this means that f of x times x squared minus f of x 2 equals 0. And this is much easier to work with, I think you'll agree. The reason it's much easier to work with is because this is already a factor. And so I have, I have f of x times x squared minus f of x equals 0, right? Why? Because we go here and we look at this 2 is not relevant, so we can just multiply both sides by 2. And 0 times 2 is 0. So we have this. And for those of you who've done quadratic equations, you might see a sort of similar theme here. So we're going to have f of x equals 0 or f of x equals x squared. So there ended up being the solution which we didn't notice at the start. Why is that? Because we were trying to focus more on the form of the method, right? But in general, some things you should check for are some known algebraic identities. Right? Like in this case, we have this identity popping up, right? Which you might recognize. So you might want to look out for algebraic identities hidden within the statement, and you might want to check out some polynomial functions. And at the same time, you might want to check like 1 by x type stuff. In the case that your function is from positive reals to itself, for example. I'll just get out of the way so you can read it. So these are some things you can check for to determine some solutions. Okay, so we have f of x equals 0 or f of x equals x squared. But are we done? And I want you at this point to pause and write down your answer in the chat. Don't be afraid if it's wrong. Don't be too confident if it's right. Like if it's right, then good. But if it's wrong, don't be afraid about that. It's normal. When I was dealing with this sort of thing, even I messed it up, right? So I dealt with it in 2008. Or you can have a look at it if you want. But this is the first place where I dealt with this sort of thing. And in fact, the answer is no. We're not done right now. Like, yes, both of these work. But what if you have some weird function which is defined like this? So you have this function which is 0 if x is rational and is x squared if x is irrational. What do you do with that? Right? Because that still satisfies this equation. F of x is either 0 or x squared in each case. But f of x isn't always 0 and it isn't always x squared. And this is known as the pointwise trap. So the question is, how do we get rid of the pointwise trap? Right? And the way we do this is, and there's a weaker version where you assume f of a equals 0 and f of b equals x squared and show that it doesn't work. But instead, what we're going to do is let a be the set of a such that and b be the set of b such that f of b is x squared. Right? Because we know that our function is of the form 0 for some x and x squared for some other x. And x squared for some other x. So this is just another way to write that. Yeah. And it's fine if you take some time to figure out what I mean. It took me a decent amount of time as well. So now the question is, what happens if you plug in an a from a and a b from b? Right? And let's do that. So we get f of a. So if I take x as a and y as b, right? Then what I'm going to get is f of a plus b equals f of a square minus b plus 4 f of a b. But we know that a is in this set capital A. So f of a is 0, which means I can get rid of this and I can get rid of this entire term. Alright? I hope we're good so far. Which would mean that f of b equals f of a square minus b. Alright? Now b belongs to the set capital B. So then this is equal to b squared. Alright? So since, okay, and one more thing I have to assume is that b is not equal to 0. Because if b is equal to 0, then it's going to be in both of these. So we just assume b is not equal to 0 to get rid of that. So since f of a square minus b is not 0, because it's b squared, we must have that this is equal to a square minus b whole square. Is that cool? I hope that's cool. Which means that a square minus b whole square equals d squared. Has to always hold. Yeah? Good. So far. We're happy. And if we want, we can just simplify it further. Right? A to the 4 minus n. Like, we don't need it. Okay. Now here's one of the key ideas. One of the sets, capital A and capital B, is infinite, right? Now, we have two cases to make. First of all, if capital B is infinite, then I highly doubt this can hold for all A, because that will make it an algebraic identity, pretty much, because we have a polynomial equation, right? And if A is infinite, well then it obviously can't hold, because we have some fixed quantity is equal to some infinite number of things squared. And some infinite number of things squared has to lead to some infinite number of things. Why? Because this is your graph of x squared, and at any point you're only going to get two values. You are not going to get infinitely many. Alright? You can, so the case A equals an infinite set is doable. I'll leave the case where B is infinite to you, just so that you get a sort of idea of how to deal with it, and also so that you kind of feel like you finished the problem yourself, because that's a good feeling to have. So now our next problem, and this problem happens to be from 2015 Middle European Maths Olympiad. I would not be surprised if you haven't heard of this Olympiad, because it's not that well known, but it's a pretty good Olympiad. So the problem asks to find all surjective functions. I'm assuming you know what surjective is, because this is the prerequisites. Surjective function f from the naturals to the naturals, such that for all positive integers a and b, exactly one of the following equations is true. So now we're going to get a kind of spiced up FE. Because if you look at the previous example, this was just one straight equation. But now we have a bit more complexity. We have two equations. And at any point, only one of them can hold. Okay? They've given you the definition of surjectiveness. And just to be clear, for every y belonging to the range, there exists some x belonging to your domain. Cool? And we have these two conditions to deal with. So there are multiple things to look at here. First is decoding these conditions. Second is decoding why there's surjectivity in the first place. Right? So let's start with decoding the surjectivity condition. And when I think of surjectivity over the natural numbers, that means if I consider f of 1 then I just get the natural numbers. That's what it means in this case. So now the question becomes, what if I consider the value of x for which f of x equals 1? Alright, and this is why I like FEs a bit. more than normal because most FEs seem to be quite algebraic in nature. But this FE in particular, I feel is a bit more combinatorial in nature, maybe number theoretic also, because you might recognize this as the extremal principle. As the extremal principle. I mean, I kind of think of it as wishful thinking, but you might recognize it as the extremal principle, which is something you use in combinatorics. But that reminds you to just keep your eyes out, keep your eyes open for any sort of idea at all, right? So what if we look at the x for which f of x equals 1? Well, first of all, what if that x happens to just be 1, right? Then f of 2 is not equal to f of 1, right? Why? Because f of 1 is equal to f of 1. And f of 2 cannot therefore be equal to the minimum of f of 1 and f of 1. Right? Because since this equation holds, this equation cannot. I hope it's clear. Okay then. And in general, if you look at it, you can just say that f of 2x is not equal to f of x. So this is one piece of information which I'm going to put on the side for now. Yeah? So one piece of information to put on the side is that f of 2x is not equal to f of x. Nice. Progress, right? Okay. So what if x is not 1? Maybe. Like, we've looked at beta x equals 1. Yes, we could look more. But just because, what if x is not 1? Well, then f of x plus 1 has to be equal to the minimum of x and f1. Why do I say this? Well, let's choose the minimal such x, right? Because it's possible that f of 1 is 1 and f of something which is not 1 is also 1. So let's just choose the minimal value. Again, more extremal principle. Let's choose the minimal x so that f of x is 1, right? And the advantage that gives you is that means that f of 1 is not equal to 1, right? So then f of x plus 1 then has to be equal to the minimum of f of x and f of 1, which is 1 because f of x is 1. And you can't go any lower than that. So f of x plus 1 is 1. Similarly, f of x plus 2 equals 1. And you just keep going down, right? So f of everything which is at least x has to be 1. But, well, f is subjective. So if I look at my number line, and let's say I have x here, and here onward, f of everything is 1, then I really only have finitely many values over here that f can take. And if f takes some finitely many values, sorry about the captions, if f takes some finitely many values, there is no way it covers the entire set of natural numbers, is there? Right? And what this investigation leads us to, what this detective work leads us to, is that f of 1 equals 1. Now, what does f of 1 equal to 1 give you? Because you need to use this information somehow. And that's another heuristic, by the way. Using your information that you have just obtained to get more information is a crucial idea in these cases. So f of 1 is 1. Obviously, there will exist some x. In fact, f of 2 is then not 1, as we discussed. Right? So from here we get that f of 3 is f of 2 plus 1. And since f of 2 is not equal to f of 1, this has to be equal to the minimum of f of 1. So this is equal to 1. And if you keep going on like this, what you'll notice is that f of odd is 1 and f of even is more than 1. Let's try it again. F of 4 is f of 3 plus 1. Right? But f of 1 is f of 3 and 1. So then f of 3 plus 1 cannot possibly be 1 because that would violate the fact that only one of these holds. And if you keep doing this, you're going to end up with this, which is nice because we're done with half of the natural numbers. But which is also not nice because we're left with the even numbers. Right? Cool. So now let's deal with f on the even numbers. Yeah? And now what I'm going to do is I'm going to define a function g of x, which is defined so that g of x equals f of x over 2 minus 1. And I'm going to define this over the even numbers. The reason I'm going to do this is because now we've gotten rid of 1. And ideally, we'd want our condition to work again about surjectivity, because that is going to help us in solving the problem, because we just used it and we want it again. So what I do is I define this from the set of even numbers to itself. This is not standard notation, by the way. So I define g from the set of even numbers to itself as f of x over 2 minus 1. Two things it does. It brings it back to the natural numbers. Sorry, this is back to me. It brings it back to the set of natural numbers, and secondly, 1 is included. So f is still surjective now. Right? And here's the kicker. We're going to have that g of x equals g of y. Okay, wait. This is meant to be 2x, I believe. Oopsies. My bad. So this is... Okay, it's fine. Mistakes happen. So g is going to be from the set of naturals to itself, where g of x is f of 2x minus 1. Why? Because everything is back to the naturals. This is going to go back to the naturals. And secondly, 1 is included, so f is surjective again. Hooray! Now, the kicker here is that g of x equals g of y. If and only if f of 2x equals f of 2y. Yes? And at the same time, if you look at this condition, it is also satisfied by g because it's satisfied by f. So f of 2x not equal to f of 2y if and only if f of 2x plus 2y. I'll just get into this side. F of 2x over 2y is equal to min f 2x f 2y. Make sense so far? Cool. And in fact, you'll notice that if I write this down in terms of g, all I'm going to get is g of x not equal to g of y into if and only if g of x plus y is equal to min of g of x and g of y. And why this happens is because magically these minus ones that we put on the end happen to cancel out when they're both put in the LHS and the RHS, right? So now we have a function g from n to n, which is surjective, and it satisfies this exact equation. So we know that g of r equals 1, which means that f of 2 mod 4 minus 1 equals 1. So f of 2 mod 4 is equal to 2. And in fact, you can keep defining functions g like this, right? Because we're done with 1 mod 2. We're done with 2 mod 4. Now, if I look for 4 mod 8, I can just define this the same way, except I can write g2 of x as f of 4x minus 2, right? And when I define this function g, it's going to satisfy the same properties as above due to the same cancellation logic. And I'm going to get that f of 4 mod 8. So f of 1 mod 2 is 1, f of 2 mod 4 is 2, f of 4 mod 8 is going to be 3, right? And in general, if you end up f of 2 to the k mod 2 to the k plus 1 is going to be equal to k plus 1. Are we done? Kind of, but we can do better. There's a better way to write it. So what do I mean when I say that something is 2 to the k mod 2 to the k plus 1? What I mean is that 2 to the k divides n, but 2 to the k plus 1 does not. Right? And using this to our advantage, we can say that every single natural number comes under one of those buckets of 2 to the k mod 2 to the k plus 1. Alright? And then we can just prove that our function satisfies this, which I need as an exercise. But if you want a keyword related to this, look up this VP. The basic idea is VP. So in particular, V2 of x is the largest k, largest k with 2 to the k over n. And so you can just conveniently write down our function as V2 of x plus 1. And at this point, we can check these two words, but okay, I'm just going to check it for you guys anyways. And I'll erase this for now. Okay, should I? That's fine. I'll erase this for now, just the middle part. You can go back to the video if you want to have a look at it again. And I'll just do it really quick. So let's say V2 plus 1 is not equal to V2 of y plus 1, which would mean that V2 of x is not equal to V2 of y, right? So then x is going to be 2 to the a times m, y is going to be 2 to the b times n, where a is not equal to b. X plus y is going to be, okay, let's say a is greater than b without loss of generality. X plus y is going to be 2 to the b n plus 2 to the a minus b n. Note that m and n have to be odd. So this is odd, but this is even. So this whole thing is odd. So then v2 of x plus y plus 1 equals b. Wait, does it equal b plus 1? Yes, b plus 1. And in particular, v2 of y is also b plus 1. And that happens to be the minimum among these two, because for this one it's going to be a plus 1, for this one it's going to be b plus 1. Right? And you can check that if you have 2 to the a m, 2 to the b n, with a equal to b, so I'll just write this a anyways, then we're going to substitute 2 to the a times m plus n. But since these two are odd, this whole thing is going to be even, which means that you have some more 2's to carry over here, which means that the v2 will increase. Okay, that was a good question. Let's move on. Prove that there is no function f, the set of non-negative integers into itself, such that this is a gem of a problem. I love this problem so much. And a bit of historical story. I was first shown this problem in my INMO training camp, and it uses this new idea, which I don't think I've seen covered much anywhere else, known as arrows. So don't be surprised if you haven't heard of it. But it's a really nice idea, so I think I'm going to introduce it here. And if you want the source of the problem, then this is from the 1987 INMO, I believe. Yes. Okay, let's try this. Basic first principles. How can we utilize this condition? Plugging stuff in probably won't help, right? Because we have an f of f. And the issue with having an f of f is that it doesn't really give us much information about f. Okay, so what else can we do? Well, what if we just try to induce this condition as much as possible? Right? This is our next heuristic. Just trying to use a condition as much as possible. So what if I just add on another f? Well, if I look at f of f, I can write this in two ways. I can write this as f of f, or I can write write this as f of f of. And this gives you two quantities you can compare. So if I look at this is going to be f of n, this 1987. Whereas if I look at this other quantity, this is going to be of this 1987. All right, this is good. So now we have some more information to work with. I'll forget this right here. F of n is 1987 equals f of n is 1987. Good. So as you can probably see by now, the main idea of FEs is just to gradually get more and more information about the function until you can break it down, right? So now we have one piece of information. The question is, how do we use it? And this is where we use our arrows philosophy. So the way this works is, okay, if you have a function f over some set, the way you can look at it is, you can look at these dots or these vertices, and you can label them as the elements of the set. And you can draw an arrow from one to the other whenever f of that thing is that thing. So this arrow would mean that f of 1 equals 2. This arrow would mean that f of 2 equals 3. This arrow would mean that f of 6 equals 3. And this is going to come in handy. Why will it come in handy? Well, let's do the same idea. N plus 1987. N plus twice 1987, and so on. We kind of have a chain, right? Because f of n plus 1987 is f of n plus 1987. And this is going to be this plus 1987. So one thing you can think of doing is taking the equation modulo 1987. And if you do that, you end up not having to worry about the pluses, right? So you're just going to get direct arrows. And you can directly jump them up. Oh god. Yeah. That should be alright. And you can directly join these like this. Or like this. They're the same. Pretty much. Right? But for now, we're going to keep the plus 1987s because they're fun. And now what? Now we're stuck. So if you want, you can pause the video and you can try it out. This is a hard problem. So just chill out and try it. And in the meantime, I'll try to recollect this. So you're going to see a bit of how I try to do things in contest, I guess, which is fun. So far we have f of n plus 1987 equals f of n plus 1987. Okay. One more thing that we have, and this is a very basic thing, is that f is injective. Why is f injective? Well, if f of A f of B, then the same holds for f of A and f of B. And then you use this condition. So A plus 1987 equals B plus 1987. And these cancel off. So A equals B. So f is injective. That's another thing we have. Question is, can we use these things somehow? And at this point, you might want to kind of look at the chains, modulo 1987 again. So if I have some remainder R, then I go to 1987 for some, and so on. So twice 1987 plus R, blah, 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 blah. Then I'm going to get these sort of chains, right? Where this is going to be this plus 1987, this is going to be this, and out of 1987. And because f is injective, you'd expect this to kind of cover most of the things modulo 1987, right? And if you draw the normal graph, we're going to see that these two are going to fall in the same residue class. These two are going to fall into the same residue class. And if you keep going like that, you'll notice that we kind of have a pairing off of residues for 1987, right? So, in particular, what that means is that f of 1 mod 1987 is going to be some r, f of r is going to be equal to 1. Both of these are mod 1987. And in particular, f of 1 is not going to be equal to any s for any s equal to r. So, kind of you're forming a bijection between residue classes. You're pairing them off. So 1 gets paired with r, 2 gets paired with something, 3 gets paired with something, and so on. Right? But that means because 1987 is odd, one of these residue classes has to go unpaired. And the issue with that is that would mean that of that residue class is going to be the same thing on 1987. But that is not bad. Like, come on, it's good. We're going to have some nice thing. Here's the issue. F of r is r plus 1987. Right. So when am I going to fit f of r? Like if I look at the smallest element, it is going to go to something which is the same residue. That is going to go to something bigger. But this is going to go to something bigger. And this is going to go to something bigger. I'm looking at jumps of 2 now. So if I go based on jumps of 2, we're going to keep getting to bigger and bigger stuff. Right? And this is an issue. Why is it an issue? I don't remember. I suddenly blanked out. Let's see. Can I make a new slide? Okay. Okay, guys, just cut this part off from the editing, please. Let me try to move this up. Yeah, just cut out this part. Okay. So just to give a recap, what have we done? We've shown this by a sort of double counting argument in a sense. We've shown that f is injective. We've noticed that there's a sort of pairing of residue classes for 1987. So we noticed that because 1987 is odd, one of the residues must be unpaired. So far, so good. Good. So if we have some r, then we're going to get to f of r, we're going to get to f of r, and all of these are going to be the same on 1987, right? And the issue with this is that if I look at the smallest residue, this immediately jumps over here and takes a big jump of 1987. We have another jump of 1987 to move to more, right? So what I mean to say is that if f of r is r plus k times 1987, then we kind of have an issue because after k such jumps, we're going to reach to the same value as f of r, which would mean that eventually we have to cycle back somehow. But there's an issue with cycling back. We can't cycle back to get this f of r because we want our graph to go infinitely far away. Because if you remember, f is going to take pretty much all large values. So we can't have a graph cycle. So it must keep going straight. But we can't have it go straight, because it must get to f of r at some point. And that's a contradiction. So, yes, arrows, super important, super fun. If you want some more arrows practice, you can try 2014 INMO shortlist, if you've heard of it, and 4. So INMO is a competition which is held by the USA MLP team, as far as I remember. So you can try its shortlist, number 3, problem 4. Okay, good. So let's do a quick recap. We started out with this problem for the around DST, which taught us basic substitutions, it taught us to guess functions, and it taught us to try to simplify calculations by cancelling stuff out. And it also featured this beautiful idea of pointwise trap. After this, we moved on to this problem from the 2015 Middle European Math Olympiad, which taught us how combinatorial ideas can be important in FEs, especially stuff like wishful thinking, which you will often see in combinatorics problems, and how you can try to simplify things by defining these functions. Now we move on to this from the 1987 IMO, which teaches a very new idea in the form of arrows. We learned how the sort of rough representation of a function can help us solve things and also help us visualize these functions. All right. So this is your homework problem for the day, and it is from the 2013 Benelux Math Olympiad. So the Benelux Math Olympiad is an Olympiad which, again, not many of you have probably heard of, but it has some decent problems, and I think it's a good source for INMO preparation in particular. And the reason I chose this problem is that instead of an equality sign, you have a less than or equal to sign, right? And some people are pretty scared of these sort of variations on functional equations, when the reality is that these inequations are often combinatorial type problems, or often even geometric problems in functional equations, are actually just the same thing as a normal FE. The base principle is the same, except that there's a little more flavor which you have to adjust. Like, I know these people, and they're scared of functional inequalities, and they want specific resources for that. And for that, my advice is think of it like this. If you do combinatorics, you will come across many types of problems. You'll come across combinatoric games. You're going to come across some sort of minimum, maximum things, find the minimum number of times, find something. You're going to come across counting problems. You're going to come across so many different types of combinatoric problems, right? And here, the difference is that the underlying structure is the same, but you need to be somewhat creative in your approaches. And I believe on this note, I will end. Enjoy your vacations, enjoy your school after that, enjoy life. Okay, bye. Oh, and don't forget to subscribe, of course.